Myself, Dr. Naresh Kumar, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In last lecture, we have discussed about concept of scalar, point function and vector point function. What is scalar function? Point function means what is the value of the function at any point in a coordinate system, three-dimensional coordinate system. And vector point function, what is the value of function in a vector form? In a vector form, what is the value of the function of any point in three-dimensional coordinate system? So in last lecture, we have discussed these two topics in detail. But now, today, in this lecture, I am going to discuss a very interesting topic, very important topic, gradient of a scalar field. What is gradient of a scalar field? Or what is grade of a scalar point function? If we discuss about grade, then there should be a scalar point function, never vector point function. Gradient work on only a scalar point function at any point in the coordinate system. So we want to discuss in detail about a gradient of a scalar field or a scalar point function. Before starting our topic, I want to again discuss some basic concept of a scalar point function and vector point function. Then I will discuss a new topic, gradient of a scalar field. So first of all, what is a scalar point function? I want to discuss about a scalar point function. Some elementary definition I want to give. So a scalar point function, that is the position of a point in the function form, means the value of the function at any point in the coordinate system, three-dimensional coordinate system. What is the value of the function at any point? Point is given. Then what is the value of the function? So suppose in any coordinate system, this is x, this is z and this is y. This is coordinate system. Okay, three-dimensional coordinate system. And this is the point P in this system. This is point P and the position of the point is x, y, z. So now this is the position of the point. What is the function at this point? So value of the function at this point is f, x, y, z, where x is some function of t, y is also some function of t and z also some function of t. X, y, z are function of t. So this f, x, y, z is known as a scalar point function or a scalar function in three-dimensional at any point. So a scalar function f, x, y, z is a function which is defined as each point, every point. Every point has own function in a certain domain D in space in three dimensions. Its value is real and depends only on point P, x, y, z. Position of a point is P, x, y, z. Then value of the function at P, function x, y, z. Function means there is some relation in x, y, z, but not on any particular coordinate system being used. Not any particular coordinate, any coordinate system. Next, second is vector point function. What is vector point function? So basically, definition of a vector point function is the value of the function in the vector form at a given point in the coordinate system. In the three-dimensional coordinate system, value of the function at a given point in three-dimensional coordinate system, value of the function. Value of the function at a given point in a three-dimensional coordinate system, that is known as a vector function. If value of the function is vector form, that is known as a vector function. If value of the function is scalar form, that is known as a scalar point function. So there are only two types of function. First is scalar point function. Value of the function is in a scalar form. There will be no use of vector. And vector point function, the value of the function in vector form at a given point in three-dimensional coordinate system. If each value of a scalar variable x, y, z is t, x is also some function of t, y is also some function of t, and z is also some function of t, then correspond a value of a vector r. Vector r is called vector function of the scalar variable t, and we write vector r equal to vector rt. R is some function of t. R is vector in t form. So r vector is equal to function of t vector. For example, the position of vector r of a particle moving along a curved path is a vector function of time t, where t is scalar. Since every vector can be uniquely expressed as a linear combination of three fixed non-coplanar vectors. Three non-coplanar vectors. What is three non-coplanar vectors? Three non-coplanar vectors, therefore we may write vector function t. Vector function t equal to f1 ti plus f2 tj plus f3 tk. This is vector point function. This is given in vector form. Vector form means I, j, k form. I cap, j cap and k cap. I, j, k are three unit vectors which are non-coplanar. Non-coplanar means these vectors are not in same line. Those vectors whose direction is same, that is known as a coplanar vectors. If the direction is different, those known as a non-coplanar vectors. So I, j, k vector are three vectors which are mutually perpendicular to each other and intersect at one point. So here basically I have given one example like this. Okay, this is x-axis, this is y-axis, this is z-axis. So this point is, this is I vector, along x-axis known as a I vector, along j-axis known as a j vector, j cap, unit vector j, along z-axis known as a k vector. So here I, j, k are three non-coplanar vectors. They are not in same direction. They are in different direction. Those vectors whose direction are same is known as a coplanar, and direction are not same means non-coplanar vectors. So I, j, k are three non-coplanar vectors, unit vectors. So in this system, in this coordinate system, we find out a vector function is known as a vector point function. How we can discuss a vector point function? This is any point P. Okay. And here position of this point is x, y, z. So this is OP. OP is, this is origin. Coordinate of this 0, 0, 0. This is OP. This is tail and this head. OP is vector R. This is vector R. So now, what is vector R? Vector R is equal to, first of all, we go to OA. OA. OA is X. X distance. X is the distance covered on X axis. OA. Next is AB. This is V. This is Y distance along this axis. This is J vector along Y axis. This is parallel to this. Okay. This is parallel to this J vector. So this is Y. And this is K vector. BP. This is K vector. And this value is Z. So first of all, I am starting from here. The point is starting from O and reach at A, OA. OA then OB. OB then BP. Then position is this XYZ. So in this case, here OA vector plus AB vector plus BP vector. So value of this R is this equal to OA. OA means XI vector plus YJ vector plus ZK vector. So this is vector R. This is known as a vector point function. Now, derivative of a vector function. How we can differentiate a vector function, vector R, with respect to a scalar T. How we can differentiate a vector R? R is vector is given in question paper. How we can differentiate a vector R with respect to a scalar T? We can differentiate one time to a vector R and we can differentiate two times to a given vector R. We can differentiate more than one time to the vector R with respect to T. So here we want to discuss a problem how we can differentiate a vector function R with respect to a scalar T. So that is important and interesting question which I am going to solve. So here is problem 1, very easy problem this. If this is Ft, function of Ft, here is missing, Ft vector function or maybe R vector. Vector R equal to this. R equal to sin t into I. I is unit vector. I is unit vector. This is unit vector. Unit vector along x-axis. Along x-axis. And mod of I is 1. J is unit vector. J is unit vector along y-axis. Along y-axis. And J ka mod is mod of J vector. This is also 1. And K is unit vector. Unit vector along Z-axis. Mod of K unit vector is also 1. I, J, K are unit vector working along x-axis, y-axis and z-axis respectively. These are unit vectors, so mod of I cap is 1. Mod of J cap is 1. Mod of K cap is 1. So this problem tells us that if any vector R is given, how we can how we can find derivative of vector R. So here vector R is this sin Ti plus cos Tj plus Tk. Then find d2R over dt2. d2R R vector over dt2 and mod. How we can find the value of this? So now start solution. We have given vector R. This is vector R. Vector R is given this sin t into I cap, and cos t into j cap, and plus t into k cap. This is equation 1. This is given in our question paper. This is the vector point function is R. R is the sum function of vector point function. This is in vector form. I, J, K are present in our equation. So we can say this is vector point function. So now differentiating with respect to t. This vector R is the function of t. T is some scalar. So differentiating with respect to t, two equation one on both sides. Then we get differentiating with respect to t. T is scalar here. T is scalar. So dr over dt, d vector r upon dt equal to differentiate with respect to t. Differentiate with respect to t means d over dt. This is ordinary differentiation. Ordinary means there is only single independent variable t. Vector r dependent on a single independent variable t. So d over dt equal to sin t into I plus cos t into j plus tk. This is vector r is given in question paper. So again this implied that d vector r over dt equal to, now this differentiation with respect to t taking inside the bracket with each function. So there are three terms I, j and k. So d over dt means differential with respect to t of sin t, I is vector, and plus d over dt of cos t, j is vector, and plus d over dt of t, k is vector. So this implied that dr over dt equal to d over dt of sin t, d over dt of sin t, this is cos t, and d over dt of cos t, this is minus sin t, minus sin t. So writing this formula here, differentiation of sin t with respect to t is cos t into I. Differentiation of cos t with respect to is minus sin tj, plus differentiation of t with respect to t is 1. So we write here k. I cap, j cap, k cap, cos t minus sin t and plus k. This equation 2. Again differentiating equation 2 with respect to t. Again differentiating, then we get on both sides, left side and right side. In equation 2, there is first order derivative of vector r. First order derivative of vector r is dr vector over dt. Now again differentiating this vector, then we get 2 time differentiation of vector r. Then we get d2r vector over dt2. d square r vector over dt square means 2 time differential of vector r. So again differentiating equation 2 with respect to t. Then d over dt, I am writing here this equation 2. 2 is this equation. So cos t into I cap minus sin t into j cap plus k cap. So now d2 r vector over dt2, d over dt, differential with respect to t, d over dt taking inside the bracket with each function. We differentiate a vector r with respect to t, then we differentiate each term with respect to t. So d over dt of cos t. Here is cos t, yes. And minus d over dt of sin t plus d over dt. Here is only k. In last equation, third term, we see that there is only k vector. K vector here, but there is no function. So here is unit 1. One function is there. So we differentiate with respect to t 1. So d over dt, we know this 1 is 0. So differentiating with respect to t cos t, that is minus sin t, into I vector, and d over dt of sin tj, this is cos tj, and d over dt of 1, that is 0. So putting here 0k. So this is 0. Basically d2r vector over dt square equal to minus sin ti minus cos tj and 0. This is 0. This is equation 3. This is second order derivative of vector r. This is second order derivative of derivative of vector r with respect to t. Now finding value of this. This is the mod of d2r over dt2, modulus. So this implied that mod of d2r over dt2 equal to mod of minus sin ti and minus cos tj. So what is mod? Mod means suppose here ai cap plus bj cap plus cj cap ka mod. We want to find the mod of this vector. This is any vector r. Okay. So now mod is under root. Coefficient of I unit vector. Coefficient of I is a square, a ka square. Coefficient of j is b ka square. Coefficient of k is c ka square. So this is mod of a square plus b square plus c square. This is modulus of a vector ai plus bj plus ck. So similarly we can find here the modulus of this d2r vector upon dt square mod of minus sin t I cap minus cos t j cap equal to under root. I ka coefficient of I is minus sin t ka square, and coefficient of j is minus cos t, here is minus cos t. So after squaring, under root sin square t plus cos square t. So this is under root 1. This is under root 1. Under root 1 is 1. So d2r vector upon dt square, this is the value of mod of this is 1. So this is answer. Okay. Now next topic is grade of a scalar field, scalar vector, scalar function or scalar field. Grade. What is grade? How we can define a grade of any scalar point function? So let here phi xyz. Phi xyz is a scalar point function which is given at any point in three-dimensional coordinate geometry. xyz is the point. What phi xyz is the function at that point in the three-dimensional coordinate system. So function, a scalar point function is given at every point. Every point has own scalar point function. So phi xyz be a function defining a scalar field. Phi xyz is a function defined a scalar field or a scalar point function, or basically we can say function. Then the vector dou phi over dou x into I plus dou phi over dou y into j, dou plus dou phi over dou z into k. This is known as a I, j and k. I, j, k are unit vector along x, y, z respectively. These are non-coplanar vectors I, j, k, where this is differential operator, three-dimensional differential operator. This is known as a three-dimensional differentiation operator. Differential operator. Three-dimensional differentiation operator. This is del. So this value of this is I dou over dou x plus j dou over dou y plus k dou over dou z. Okay. With I differentiation with respect to x plus with j differentiation with respect to y plus k differentiation with respect to z. Because k is a unit vector along z axis, so we differentiate with respect to z. I along x axis, so we differentiate with respect to x. So it is known as a three-dimensional three-dimensional differentiation operator. Three-dimensional differentiation operator. This three-dimensional differential operator. Differential operator. Okay. Now, this is known as a del. Del equal to I dou over dou x plus j dou over dou y plus k dou over dou z. Del is, this is operator, three-dimensional differentiation operator is known as a three-dimensional vector differential operator. Vector is also, this is a vector. This is always a vector. Three-dimensional vector differentiation operator. Del phi, this is also known as a gradient of a scalar field. Okay. Del is known as a nebula. This is known as a nebula. This is called a nebula. So now, thus, grad phi equal to nebula phi. This equal to I dou over dou x plus j dou over dou y plus k dou over dou z. And phi is the scalar field, scalar function. This is how phi is some function of t here. Okay. This equation 1. The gradient of a scalar field phi is obtained by operating on phi by the vector operator. Vector operator means nebula. If we operate by this any scalar field function, then we get gradient. So del is this. Now we want to solve some problem based on gradient of a scalar field. How we can solve a problem? So problem 1, find grade phi. In this problem we find out the value of grade phi. Grade phi means nebula phi. Nebula phi means phi is given in our question paper. And we operating the function phi, scalar field function, with three-dimensional vector differentiation operator. So here, when phi is given by phi is 3x square y minus y cube z square. This is the value of the phi. This is known as a scalar field function. At the point is this 1 minus 2 and minus 1. This is the point. Point is 1 minus 2 and minus 1. This is the point. At this point, we find the value of grade phi. Now start solution. We know that formula for gradient of a scalar field phi, scalar field function phi is given by. We have discussed just in last slides what is grade phi. We have discussed about the formula of grade phi, gradient phi. Phi is scalar point function. So this is represented by del phi. This is del. This is nebula, represented by this nebula. This is vector function. And phi is some function in x, y, z. So now here grade phi equal to putting value of del. Del is nebula. So this is three-dimensional differentiation vector operator. So value of this del here, del is this equal to I cap dou over dou x plus j cap dou over dou z y plus k cap dou over dou z. Okay. This is the nebula, value of nebula or three-dimensional differentiation vector operator. So now we operate this by phi. Del phi. So putting value of this operator, this I am writing I cap I unit vector dou over dou x plus j cap j unit vector dou over dou y plus k cap k is unit vector along z axis and dou over dou z. And out is phi. Phi is some function of t, function of x here, function of t. This is x, y, z function of x, y and z. So now this is the value of nebula. We have already write this. So grade phi grade phi. Now taking phi inside the bracket. Here phi is outside the this operator. Now operating this phi. Phi goes inside the bracket. Then this is differentiate with respect to x, y and z in each term respectively. So now after multiply, this means not multiply, this is operator. Operator means when we multiply by phi inside the bracket, then phi differentiate with respect to x, y and z respectively in each term. So I cap dou phi over dou x plus j cap dou phi over dou y plus k cap dou phi over dou z. This is equation 2. Putting the value of phi in equation 1, in equation 2. So here I dou over dou x, this is value of phi, and plus j cap dou over dou y, this is equation of value of phi, k cap dou over dou z, this is value of phi. Now in first term we differentiate with respect to x. Y and z are constant. Y and z are constant. So this function is 0. There is no x. In this function is no x. Only first function is x. 3x square. So dou over dou x of 3x square. Differentiation of 6x. X square is 3 into 2x means 6x. So I am writing here I cap 3 x square means 2x. Here is 2x and y. This result is 0. Now next second term differentiating with respect to y. Y in present in both terms. So here 3x square y is 1. Dou over dou y of y is 1 and y cube. So dou over dou y of y cube. This is 3y square. So we write here 3y square z square. Z is constant here. And in multiply. So no change in z square. Plus k cap. Here differentiating with respect to z. So this first function there is no z. In this function is z square. So y cube is constant. Differentiation of z square is 2z. So here is 2z minus 2z y cube. Now putting value of x equal to 1, y equal to minus 2 and z equal to minus 1 in equation 4. From equation 3. Then we get here grade phi equal to. So we get here grade phi equal to minus 12y minus j minus 6k. Grade phi is equal to this equal to minus 12y cap minus j cap and minus 6k cap. Okay. So this is grade. Now next I want to second problem depend on gradient. Here r is scalar. R is a scalar function. So now solution start here. Solution. Here given us that this is nebula del r to the power n. R is scalar function. This equal to n r की power n minus 2 into vector r. Okay. This is proved that. We want to prove this equation 2. Now TLHS means taking left hand side. Left hand side means del nebula and r to the power n. R is scalar vector. R is scalar point function. R is scalar point function. R is scalar point function. So what is value of r here? R is vector r. R is vector r xi plus yj and plus zk. Okay. So now mod of vector r. Mod of vector r is mod of xi plus yj and plus zk. So mod of is under root x का स्क्वायर प्लस y का स्क्वायर प्लस z का स्क्वायर, mod of vector r. So this is scalar r. This is converting after taking mod of vector r, that is converting small r. Small r is scalar. We are taking mod of r vector. So that is under root x square plus y square plus z square. Okay. So this is r. This is scalar. R equal to x square plus y square plus z square whole to the power half. This is vector r. R equal to x square plus y square plus z square whole to the power 1 by 2. This is r. R is scalar. After taking mod of vector r is this. Here vector r is xi plus yj and plus zk. Now taking mod of this vector r. So vector r is, mod of vector r is r. Mod of vector r is r. So this is scalar point function is given in our question. So now this equal to, this is del operator and this is scalar. So there is no dot product. Here putting value of r. R is x square plus y square plus z square whole to the power half and whole to the power n. So now this is del, here x square plus y square plus z square whole to the power n by 2. This equation 2, one this equation 2 and this equation 3. Okay. This 3 putting here. So now del r to the power n, this equal to del, putting value of del I cap dou over dou x plus j cap dou over dou y plus k cap dou over dou z, and putting value of r x square plus y square plus z square whole to the power n by 2. Now this taking inside the bracket, then here I cap dou over dou x and differentiating this x square plus y square plus z square whole to the power n by 2. Differentiating this with respect to x and plus j cap dou over dou y and x square plus y square plus z square whole to the power n by 2 and plus k cap dou over dou z and x square plus y square plus z square whole to the power n by 2. Okay. So now this is the value of this. Del is this is vector del. Del is always vector. This is scalar. So now I cap differentiating this with respect to x. So here power taking before n by 2 and x square plus y square plus z square whole to the power n by 2 minus 1 into 2x. This power comes before this function and one number is less from the power. So we apply here formula plus cap j cap and differentiating this n by 2 x square plus y square plus z square whole to the power n by 2 minus 1 into 2y with respect to y plus k cap and here n by 2 x square plus y square plus z square whole to the power n by 2 minus 1 into 2z. So this function differentiating with respect to x, y and z are constant because we are differentiating partially. So we differentiating partially with respect to x, then other variable are constant. So we differentiate only with respect to x. First of all, we apply the formula of power. Which formula apply here? D over dx of x to the power n x to the power n minus 1. Basically this formula we apply here. or d over dy x to the by to the power n. So n by to the power n minus 1. So in each term we apply this formula. So this function is common. So here n by 2 is common and x square plus y square plus z square whole to the power n by 2 minus 1 is common. And here is 2 is cancelled. We see that 2 is cancelled here. So here 2 is not there. So n is common. This common. So here is xi only is xi and plus y j and plus z k. So we write here n and this x square plus y square plus z square whole to the power n minus 2 upon 2 and this xi plus yj and plus z k. This is our vector. Vector r is xi plus yj and plus zk. So putting this value here, then we get next n x square plus y square plus z square whole to the power n minus 2 by 2. This is power. Del r to the power n. This equal to n x square plus y square plus z square whole to the power n minus 2 upon 2 into vector r. So now n x square plus y square plus z square, this whole to the power half and whole to the power n minus 2, breaking this power 1 by 2 and n minus 2, this power. So here vector r. Now n, this is vector r, this is r. So r to the power n into r to the power n minus 2. This is r. R is here x square plus y square plus z square, this to the power half. This is r. Where vector r is xi plus yj and plus zk. This is r. This is r here, vector r. This is scalar r. This is mod of this. And this n r to the power n minus 2 into vector r. This is proved, r to the power n. This result is proved here. Okay. Now second problem. Problem is second is this. So second problem is del nebula and 1 upon r. This equal to, this is problem 2 and this is problem 1. So here minus vector r upon r cube. Okay. This is problem 2. Problem 2. Show that del 1 upon r, this equal to minus vector r upon r cube. How we can show this? Okay. So now same result, del and putting the value of r. R is x square plus y square plus z square, this to the power half. Okay. Now this writing in numerator and value of del I cap dou over dou x plus j cap dou over dou y plus k cap dou over dou z. And now writing value of this function. Function is x square plus y square plus z square. This taking in numerator. Then this is minus half. Minus half. Okay. Now this writing in bracket, inside the bracket. Then we can write here, this is del and this 1 upon r. This equal to I dou over dou x, and here differentiating this x square plus y square plus z square whole to the power minus half. Similarly plus j cap dou over dou y, and differentiating this x square plus y square plus z square whole to the power minus half, and plus k cap dou over dou z, differentiating x square plus y square plus z square, this to the power minus half. Now this equal to differentiating with respect to x here. So I cap and power comes before minus half, and this to the power x square plus y square plus z square minus half minus 1, and into 2x plus j cap, and differentiating again minus half, and x square plus y square plus z square, this to the power minus half minus 1 into 2y, and plus k cap minus half x square plus y square plus z square, this to the power minus half minus 1 into 2z. Here differentiating this function with respect to x, here differentiating this function with respect to y, and third term differentiating this function with respect to z. So here power comes before function and one number is minus from the power. So here we apply the formula d over dx of x to the power n and x to the power n minus 1. This formula we apply in each term. This formula with respect to x, next formula with respect to y, and with respect to z partially. So other variable taking constant. So now after simplifying, minus 1 by 2y, and here is x square plus y square plus z square to the power minus 3 by 2 into 2x. 2 is cancelled, plus next minus half into j, and x square plus y square plus z square whole to the power minus 3 by 2 into 2y, and plus k minus half into k cap x square plus y square plus z square whole to the power minus 3 by 2 into 2z. So this 2 cancel this 2, this 2 cancel this 2. So this is term is same in each term. So this is common here. So del and 1 upon r, this equal to minus common, and what is common? Minus common, and x square plus y square plus z square, this whole to the power minus 3 by 2, and bracket here xi plus yj and plus zk. This is r. R vector is xi plus yj and plus zk. This is r. And mod of r, mod of vector r is r. This is under root x square plus y square plus z square. This is x square plus y square plus z square whole to the power half. This is r. So this value putting here, this equal to minus x square plus y square plus z square to the power minus 3 by 2, and this is r, this vector r. Now this is negative power, taking in denominator minus vector r upon x square plus y square plus z square whole to the power plus 3 by 2. Here is negative power, writing in denominator plus 3 by 2. Now we can write this minus vector r upon, this is vector r upon here, x square plus y square plus z square whole to the power, this is half, and whole to the power, this is cube, we can write this type here. Okay. So now del of 1 upon r, this equal to minus vector r upon. So I have already discussed this r, where here r is r equal to x square plus y square plus z square, this to the power 1 by 2. Okay, 1 by 2. So this is writing here r. Now this is r cube, r ka whole cube. So this equal to del into 1 upon r minus r vector upon r cube. This is proved problem. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.